Hey everybody, this lecture is about limits, and we're going to call it Take It to the Limit, like the old Eagles song from the 70s. Okay, so the first thing you need to understand is the notation. If I have this funny looking thing right here, we read it as the limit of f of x as x approaches c is L. So in English, the limit of f of x as x approaches c is L. So just get used to saying that. What that means is, as x gets really close to c, f of x is getting really close to L. C is an x value. L is a y value. So your limit is always going to be a y value that it's approaching as x gets very, very close to a given c value. Now, in this section, we've got two ways of analyzing limits. The first way is numerical analysis. And so we're going to take the limit of this rational function as x approaches 2. So you may be asking yourself, well, why don't we just stick 2 in? Okay, let's try that. We'll get 2. Whoop. We will get 2 minus 2 over 2 squared plus 3 times 2 minus 10. And that is equal to 0 over 4 plus 6 minus 10, which is 0. And that, guys, isn't going to work, because remember, we can never divide by 0. So we've got to take another approach. And approach is the word. We're interested not in what f of x equals when x equals c, but what f of x equals when x gets close to c. So let's try a number really close to 2, like 1.99. Okay, I've already put the function into y1, so I'm going to go vars y-vars function y1 of 1.99. And I get 0.14306. Let's grab that, put that into our notes. There we go. Whoops. Okay. How about if we approach it from the other side? So let's do second answer. Nope. Second entry, and change that 1.99 to 2.01. Hey, we get pretty close to 0.143 again. So let's grab that, put that into our notes, and we'll be a little more patient this time as it copies and pastes. Okay, so even though the function doesn't exist at x equal 2, the limit exists, and that's a really important concept to get when you're working with limits. The function does not have to exist at x equals c. All it has to do is get close to something. And in this case, it seems to be getting close to something between 0.143 and 0.142. Okay, let's take a look at a graphical approach now. What I've done here is I've graphed the function. You can see it here. And we're interested in this section right here. So I've already zoomed in, and you can see that on either side of the graph, when x is 1.99, y is 0.143, and when x is 2.01, y is 0.1426. So it seems to be getting close to something around 0.143. Well, here's the secret. If I factor, or let me be precise here. We're taking the limit. So if I take the limit as x approaches 2 of x minus 2, and I factor, so it's going to be x minus 2 times x plus 5, check out what happens. The x minus 2's cancel, and I am able to reduce this to the limit as x approaches 2 of 1 over x plus 5, which is equal to 1 over 7. Okay, so guess what happens when we divide 1 by 7? Hey, we get a number that's between the 0.143 and the 0.1426. So that is our actual limit. All right, now let's look at another graph of a limit. In this case, we're going to take the limit as x approaches 3 of the absolute value of x minus 3 over x minus 3. And notice that if I take the limit as x approaches 3 from the left, I'm going to put a little minus sign to mean that I'm going from the left side now. That looks like the y value is negative 1. See that? Y is equal to negative 1 if I'm coming at 3 from the left. Okay, what happens if I take the limit as x approaches 3 from the right, and I'll put a little plus sign to indicate that I'm coming from the right now? Well, as I get closer and closer to 3 from the right, hey, this looks like y equals positive 1. And guys, if the limit isn't the same value coming from the left and from the right, we have to say that the limit does not exist. So that's an important concept about limits. Unless you get the same y value coming from the left as you do from the right, you have to say that the limit doesn't exist. Okay, well, in both of those cases, it was pretty clear that we had limitations on our domain because they were rational functions. What about the limit of a polynomial, where there are no restrictions on the domain? In other words, the domain is all real numbers. Well, these are great because all we have to do is plug the number straight in. So this is going to equal 3 times 1 cubed minus 2 times 1 squared plus 1, and our limit is going to be 3 minus 2, which is 1, plus 1, which is 2. And if we graphed it, we would find that as x got closer and closer to 2 on the graph, I don't know what this thing is doing, but as x got closer and closer to 2 on the graph, y would get closer and closer to 3. So we love polynomials because all we have to do is just plug the c value directly in, and we get out our L value.